We have seen how sunspots play a role in solar magnetic fields and solar flaring, and that they erratically move around, appear, and disappear. But can we tell when a sunspot is more likely to flare than others? Absolutely. And to do so, we have to utilize the magnetogram on the SDO satellite to classify the sunspots. We'll start simply with the most basic classifications. Alpha spots are usually just one sunspot by its lonesome and has just one magnetic charge or polarity, while beta class groups have at least one positive and one negative spot. This is where it's vital not to confuse the weaker surface magnetic region surrounding the sunspot umbras with a sunspot itself, as even alpha spots will have surface areas of opposite magnetism nearby. Most flares come from beta spots. Before going further, it is important to note that the northern and southern hemispheres of the sun have opposite leading sunspots. As the sun rotates left to right from our view, one magnetic polarity sunspot leads on the north, while the other leads the way on the south. They actually switch every 11 years, but we will come back to cycles of the sun later. Within beta-class sunspots is a class called gamma, where the sunspots are scattered such that the same polarity spots are not grouped together and could not be separated with one continuous line. Here you see sunspots of opposite polarity scattered about amidst a field of opposite polarity. The most important sunspot class is delta, and you need to build on your previous knowledge here. If you have a positive and negative sunspot umbra within the same penumbral region, it's likely a delta class sunspot. Delta class, like gamma class, can only come to beta regions, but gamma magnetic class is not required to have a delta spot. Technically, you just need two umbras for that, while you would need more than two for a gamma class. Gamma and delta class sunspots are more likely to have bigger solar flares, and nothing makes more flares than a beta, gamma, delta sunspot group, having a strong mix of magnetic regions scattered about. It often helps to use the intensity gram to check which spots are actually umbras and which are just the surface magnetism. Surface magnetic dots can be tricky otherwise if you just use the magnetogram. And while not a perfect system, and while more complex classification systems like the Zurich system exist, time has proven this simple classification system to be able to forecast which of the sunspot groups will produce the larger solar flares, if there are any to be had at all. It can also be helpful to note the stage in the life cycle of the sunspot. These regions can cycle the sun more than once, but often by the second time we see them, they are mature, decaying, and less likely to produce lasting flare dangers. Upon birth, these groups spread quickly and often produce many sunspots within the region, shifting the umbral fields around and likely to make delta spots, more likely to make bigger flares until stabilizing and reaching maturity. You can often tell the younger groups just by seeing its tight grouping rather than sprawling, spreading, scattered magnetics. A beta group up top, nicely spread, with a lone alpha spot below. Don't confuse the opposite polar surface magnetic areas around it. These groups are tricky. It is actually two separate beta groups that have grown so big, nearly to the point of collision. This grouping is clearly beta gamma, with the blue positive spots straddling the central negative spots. Here we see a beta gamma delta region, with the separated blue positive spot making the gamma class, also mixing on the opposite side with that red negative umbra. It gets the delta class. It is that easy. Now you can look at all the sunspots on the sun and know which ones are most likely to flare.